Hi, in this video, I'll be going through integration in now two variables and we'll see its application. And so, in the previous video, we already started off our journey into integration where we integrated over a rectangle. And we said how we have a domain that we want to integrate it over. But in the Fubini's theorem that we went through, we used integrals with constants as the limits of the integral. But not all the time that regions are always rectangles, and so there's what is known as a type 1 region, where y changes with respect to some curve. So your domain now, the y changes with respect to some curve. So it's like this, like that, or any way. But our x stays constant in this case. And so y is bounded between two functions of x. And so the integral of this domain now, you have to of course integrate the inside first. So you get a piece of this, then you integrate it, you add up all the way. So you get a piece, so you get like a strip of this. So it's like you integrate in one variable first, so y, and this will be a function in terms of x. Then because your limits is constant, this whole thing will become a value in the end. You can see now that we cannot switch the order of integration to g1, g2 of this, because we'll get a function at the end of the day. And that's not what we want. We want the volume. So we stick to the volume. What we need to do is, this thing is getting projected upwards. So it's like this, and then it go down. So we need to calculate at each point how it will be. So we need to find the volume at the base level first, then we project it up. So that's what we are doing. We integrate with respect to y first, and then we integrate with respect to x. And so we want to find the volume of the prism with bounded by the x-axis and these lines. And we can see that x changes from 0 to 1, and y, because it's bounded by y equals to x, it changes from 0 to x. And really, you just need to draw the geometric picture and you'll be able to figure out this double integral. So you just draw this, and you know y equals to x is this. Then x equals to 1 is here, and so is this region over here. So by drawing that region over here, we see that as x changes, y just takes the value from 0 to x. And so that's why y integrates from 0 to x, while x changes from 0 to 1. And by integrating this function first, you get a function in terms of x, such as 3x minus 3x squared. And then when you integrate it with 0 to 1, you get the volume of what the surface makes with the xy plane. And so this is what is known as the type 1 region. And now you might be thinking whether what is a type 2 region. And it's the analogous thing, where now x is a function in terms of bounded by two functions of y. So y stays constant, and now x changes respectively. And you have the exact same formula out, which is this. And really, it is a re-application of understanding the geometric interpretation of what the double integral is. And of course, I've already went through that the properties of the double integral for these two, and this is known as the domination property. And if you know that one of your function lies above the other, always, then of course the volume created by it will be greater than the volume created by g. You can also add domains up and take the integral over each respective domains, assuming that they do not overlap, so that you don't double count the volume. And then the integral of the function 1 will just be the area of D. Because if you think about it, the function is like your height. So if your height is 1, then of course the volume equals to area, because volume equals to height domain. So that's another way to find the area of a domain. And if we know my function is just dominated by two constants, then of course the integral will be dominated by m times the area of the domain times the capital M times the area of the domain. And really that's the application of 3 and 4. Because these are constants, so it's just whatever constant times area. And because you're dominated, this volume will be either less than or equals to the volume of F. So I hope this is all clear to you. And we'll take a look at some examples to familiarize ourselves with the double integral. And the next thing we want to take note is that in Fubini's theorem, when this a and b are c and d's are all constants, then you can just switch the integral, the order of integration, and change the limits respectively. But that's not the case when you are dealing with type 1 or type 2. And in this case, when the bounds are not constant, then the order of the integrated integral needs to be changed, the bounds. So what do I mean? So we'll take a look at this. So you want to integrate this function, but we know e to the power of y cubed cannot be integrated with respect to y. And so you need to change it to integrating with respect to x first, then y. And if you were to draw the graph out, we see that the domain is this. So now you want to vary y constantly. So y changes from 0 to 1. So y changes from 0 to 1. Then we need to think how x change. So when you have a fixed y here, the idea is you stick all the points that this line can take. And y can take from 0 to this point. And this point is really y equals to square root x over 3. So this is just square root x will just be 3y squared. And so you integrate from 0 to 3y squared. And when you work it out now, it's easy to solve. And you get the following conclusion that it equals to e minus 1. So you can see that the order of integration has changed the bounds. So they're not really the same anymore. You can't really just say it's integrate from square root. You can't really do this. Because at the end of the day, this square root x over 3 will be inside. And then it will cause a lot of problems. So you need the outside to still be the constants. So the easiest way to do this is you just draw the domain out and just see. And when we take a look at 3 variables in the next video, you'll see how this visualization helps us in changing the bounds order. So you can take a look at this example also to better understand how do you change the bounds. So for example, you want to integrate with respect to y, then with respect to x. So y changes from x to 1, and for fixed x, then x change from 0 to 1. And now you switch it, you integrate with respect to y first. So y can change from 0 to 1, and for fixed y, you can take everything in this domain. So it's 0 to y. And you can see that both integral gives you the same value of half bracket 1 minus cosine 1. And really that the reason why they give the same value is because the volumes are equal. But you can take note that the bounds cannot be switched randomly. So lastly, I'll just wrap up with some applications of this double integral. And really you can, like I said, you can calculate the area when you integrate with respect to the function 1. And so when you, let's say you have this graph over here and you want to integrate it and you want to find the area, you can just treat it as finding the volume with respect to the function 1, and you get the same integral at the end. So these are just some common applications. And of course, most applications that are very fulfilling is when you use these integrals in probability, such as you want to know the probability of of something occurring within this domain, and the functions take all the values here. Then it's just this area divided by the total area, and you get the probability. Another thing to note is you can find the average value, and it's just like the mean value theorem, but instead now you'll find the height that f averages out to, which is, so you just need to find the volume divided by the area. So that's the average height, as you say. And really, it's not much, because if you are able to find the volume, that's the main gist of the hard part. And the area is just either you integrate with respect to 1, or you just find the area using one variable calculus. So I'll leave it to you to read this example. So you can see that double integrals aren't as scary as most people think. You can really just practice a lot, and by understanding the geometric picture, you'll be able to apply it to many scenarios in other applications such as physics as well. So this is a short tutorial, and I'll catch you in the next one, where I go through now triple integrals, where it's really just extension of the double integral where you have 3 variables. Thank you and have a nice day. Bye.